Hello, this is a presentation of our ICCV paper, Black Box Few-Shot Adaptation for Visual Language Models. In this paper, we propose an efficient and black box method for few-shot adaptation of visual language models. The method is efficient, that is light and fast, and also black box, so does not require access to the model weights. So first, what are visual language models? Visual language models are models first pre-trained to minimize some distance loss like contrastive learning, so that the text and image modalities are aligned, so that given image and its description or caption, the generated text and image features match each other, so they have low embedding distance. Why you complicate? Hello, this is a presentation of our ICCV 23 paper, Black Box Few-Shot Adaptation for Visual Language Models. In this paper, we propose an efficient and black box method for few-shot adaptation of visual language models. The method is fast and lightweight and does not require access to the model weights. So first, what are visual language models? With visual language models, we first pre-train them so that we align the text and image modalities so that an image and its description have similar features in both the text and image spaces. After pre-training, one of the possible use cases is zero-shot recognition, where we can classify an image into one of the set of predefined classes by first encoding the classes with some prompt using the text encoder, so we get class prototypes, and then we classify the image into one of the classes by finding the prototype closest to the image features. But the problem with this zero-shot recognition is that we still have a modality gap even after pre-training, which is generally due to the constructive of the pre-training loss itself and the possible domain shift, where we have a shift between the test and training distributions. So in order to get good recognition results, we need a realignment step. One possible way to do this realignment is soft prompting, where we optimize some learnable vectors which are injected into the embedding space together with the class embeddings, and then we minimize the cross-entropy loss using some few-shot training examples. But this problem still have some drawbacks. First, they require access to the model weight to inject the embeddings and minimize the loss. They can be computationally expensive for large models, and they do not directly minimize the modality gap or the alignment between the text and images. In order to see if we can introduce an efficient and black box method, we can investigate if we can approximate the effect of soft prompts using a linear mapping. So first, we see if we can push the original text embeddings to be similar to the text embeddings obtained after learning the learnable prompts using a linear map. And after optimizing this objective, we can see that the obtained results are similar, either with just the linear map or with the learnable prompts. So based on this observation, we propose linear feature alignment, where we push the image features to be close to the corresponding class prototypes using a linear map. So our objective is to simply minimize the frobenius norm between the image features and the corresponding class prototypes. And to optimize this objective, LFA consists of 3 steps. An initialization step where we find the closed form solution of this problem. We regulaриze it to avoid overfitting, and then we refine it so that we can match or even exceed the results of soft prompts. So what are these 3 steps? So first, to find the closed form solution, what are the constraints so that the linear map are orthogonal mappings, and given this constraint, we can find a closed form solution called orthogonal hostess, which is just the SVD of the image features transposed the text features. Then, after finding this solution, we generally have a problem of overfitting, and we lose performances compared to the zero-shot case. So first, we do a regularization step where we push the orthogonal hostess results to be close to the identity mapping, and here we get better results. And the final step is that in order to be close or even surpass the soft prompting results, we do some refinement steps so that each image feature is closer to its class prototypes than the rest of the class prototypes. And in the end, we obtain a very efficient method with 3 steps, which generally take only a few minutes compared to a few hours with soft prompting methods, and can also match or even exceed the obtained results. So now, in terms of the comparison, here we show the few-shot image classification results over 11 image datasets, and we can see that our method outperforms soft prompting methods with between 1 to up to 1.5 points for both backbones over different visual backbones and different number of shots. Our method can also still perform very well even if the modality gap is even increased. So in case we have a big shift in the text domain, so the training and test classes are different, or what we call base to new case, and we can see that we can even obtain up to 2 points difference compared to soft prompting methods adapted to this case. And we can also match this method for shift in the image domain to the image training distribution is different than the test training distribution. Our method is also very flexible and can be used even for few-shot action recognition, where we align the text embeddings with the average of the per frame features. And we can see that our method even outperforms a soft prompting method adapted for video, where we derive some temporal aspects using some transform layers. And finally, our method can not just be used with vision language models, but also any models. So we have an encoder, text encoder, and a vision encoder, and then we can align them even if the text and visual encoders are not pre-trained jointly during the pre-training stage. So to summarize, we proposed LFA, linear feature alignment, which consists of 3 steps. First, initialization with closed form solution, algorithm to avoid overfitting, and the refinement to get good results. Our method can also be expanded to unsupervised case, where we learn both the linear mapping and the assignment, so the assignment between each image and its corresponding class. It can also be used, as we showed, with disjoint models, so not just visual language models, but any image encoder and any text encoder. Thank you, and for more details, please check out our paper and our code.